start the recording?
Yes, because we still have 1 minute, but this doesn't matter. We can start.
Started.
Just 1 minute to wait, maybe for the rest of participants. Okay, I think we can start afternoon session, and the first speaker is Alexander Kirienko, who will be talking about quantum time crystals from Hamiltonians with long-range interaction. So the floor is yours, Sasha.
Yes, thank you very much, Krzysztof, and thank you very much for organizing such a wonderful conference. I would be more happy if we are all together in Trieste, but having this online also creates a link to community. So what I will try to do today is provide a vision on quantum time crystals from slightly different perspectives that we will usually have. And specifically, I'll try to explain how can you construct a Hamiltonian that contains a time crystalline behavior. And for me, this question is very much related to the question of how do we imagine quantum time crystals. So previously, we had an amazing colloquium by Frank Wilczek, and Frank had a very visionary talk saying what happened in the past, but what happens in the future. So if we take the same vision and ask what is a time crystal, for instance, is it the fractal structure as if you Google it, or maybe it's some weird shape, or even related to Salvador Dali pictures? So what is actually the time crystal? And for me, this question is very much related. What is the underlying Hamiltonian of the system? Because if I see the Hamiltonian, I can also imagine how to build this system. And to answer this question, we need to look at definitions. And there are many definitions of time crystals. The first one, as originally proposed by Frank Wilczek, comes from the spontaneous symmetry breaking for time translation. And that draws exactly from the same translation symmetry breaking for crystals. What Frank also specifies that we want this system to be closed quantum mechanical system, but the definition may change in the future. And if we take this definition of closed quantum system, required time translation symmetry breaking, one opportunity is to use the Josephson effect and look at the current in a superconducting ring. So that's the example which was already discussed. But also, Frank had few comments in the paper, and I specifically want to read the one related to the speculations that more elaborate quantum mechanical systems whose states can be interpreted as collections of qubits might be engineered to traverse in its ground state a program landscape of structured state in the Hilbert space. And that's exactly what I will try to describe right now, that we can hope to engineer collection of qubits that behaves as a time crystal. So with persistent motion in the superconducting rings, there were a lot of discussion. Is it really a time crystal or not? Why? Because you cannot have current exactly in the ground state. So it really depends on the definition. What is a time crystal? Can you add a little bit of energy? Can you drive it or not? So there seems to be one no-go theorem. But later there was another no-go theorem formulated by Watanabe and Oshikawa. And what they did is trying to define strictly what is a quantum time crystal. So if we say there is a crystalline order that is defined by long-range correlations in space, you can take some observable phi, you can measure what will be the correlation in different points of space. And if it is a periodic function of the distance between these 2 points, and this also works in the thermodynamic limit, you have space crystal. Then Watanabe and Oshikawa said, if we have the same correlation, but at different points of time, they are periodic in time. For instance, density-density correlations where you have revivals, and it also holds in the infinite limit of the system, in the thermodynamic limit, then we have time crystals. So that's one possible definition. We can rewrite this correlation function using our order parameter, phi capital, which will be some macroscopic property of the system, evolve phi in time, and demand that it is a periodic function of time in thermodynamic limit. And what they have also found that if we do the algebra, we will see that the correlations will be limited by the Hamiltonian of the system. Namely, if we have interactions in the Hamiltonian that decay as a power law, even though the power might be very small, we cannot have formally time crystals in the closed system. And second, we also consider the equilibrium case of T equal to 0 or some finite temperature. But if we violate one of these assumptions, we may hope to get the time crystal. And I would first explain how you can get it in the stroboscopic time by adding the drive. And next, I will introduce a different way to bypass the Watanabe-Oshikawa's theorem by considering long-range interactions. So the stroboscopic formulation, as proposed in different systems, for instance, in atoms by Krzysztof Zacha and Elsa Bauer-Nayak for spin systems, we do not try to break time translational symmetry in continuous time, but instead we introduce a stroboscopic or discrete time. And here the definition will slightly change from what we had before, because we want some observable to oscillate at different points of time, of stroboscopic time. We want this to continue perpetually. And we also want to see the response at different frequencies at which we drive. So that will be a little bit similar to what Frank Wilczek defined for the superconducting current. There is a second definition, which is not non-trivial Floquet operator for the system. And why do we want this? Because we don't want a concept of time crystal to reduce to something very simple. So we demand that the evolution is non-trivial. And if you follow these two definitions, we can create the protocol for discrete time crystals. The one I would use here is take some initial state, apply the pi pulse, so just do the rotations of your spins from up to down, but then you will also evolve the Hamiltonian with Eisen interaction type. And since it is an ergodic Hamiltonian plus many-body localization, you would avoid heating in the system. So using discrete time crystal protocol, one can easily simulate this perpetual oscillation of magnetization. We can just go and simulate it. We see magnetization changes in time, and the frequency of response will be subharmonic. So you have a peak different from the frequency at which you drive. And it will be robust to perturbations. because we have interactions in the system. So that was the main feature of discrete time crystal. The system was later observed experimentally. So there are a couple of groups working on realizations of discrete time crystals, and that's not a full overview. So there are many more advances experimentally that happens since that time. So the field was really evolving and currently is evolving towards more sophisticated protocol and introducing new system how you can realize driven time crystals. If you look at the advances from the theoretical point of view, there are lots of different proposals. How can you extend the notion of discrete time crystals? And I can see that from the perspective of dynamics, it is a very interesting system to work with. And I'm working myself on protocols, for instance, of Floquet simulation. But if we look at any Floquet scheme, we always ask the question, can we find the effective Hamiltonian for this Floquet system? Usually it's possible if you have a fast drive, but in general, we can also, for any frequency of the drive, we can try to find an effective Hamiltonian, because if there is the unitary evolution, it must be generated by some underlying Hamiltonian. And my question is, what will be the property of this Hamiltonian? So that was a general interest. And can we find a family of Hamiltonians that give us this time crystalline behavior, which can now happen and continues as a continuous evolution? And that will be, again, the answer to my question, can we imagine time crystals? So how do they look like? Will it be some spooky image from Google? And I will claim that for me, it's more related to the macroscopic coupling between two entangled states and evolution of these states. So to explain how this works, I would like to return back to the Watanabe and Oshikawa condition of time crystal. And they formulated it for the closed system where magnetization the correlation function for magnetization changes periodically in time when we average over the ground state. And this should also remain true even if we extend the system to infinite size. So that's a very strict definition. And from the colloquium, Frank just said that it all depends on the way how you define the system. So here we will choose the specific Watanabe-Oshikawa condition. And we can do the reverse engineering. Imagine that this is true, that the conditions for Watanabe and Oshikawa theorem are satisfied. How can we construct such a protocol, such evolution? One way to proceed is take a state E0 and couple it to another many-body state E1 through the action of magnetization operator. So magnetization operator is non-unitary, and you will need to renormalize the state. These two states can be taken to be orthogonal. So if you act with MZ on E0, you get E1, and it should be orthogonal to E0. And the Hamiltonian for evolution of the system will be very simple. We can say it contains a projector on state E0, projector on state E1, and some other states if we use the spectral decomposition. We will also ask these states to be non-degenerate, such that we actually can observe oscillations. And next, how do we build our system? How do we get the oscillating correlation function? We can rewrite it as an action of MZ on E0 and get the E1 state. We can evolve with the unitary evolution state E0, so get our prefactor in the form of some oscillating phase, and accounting for normalization of our magnetization, we see that the correlation function reduces to the periodic time dependence, where the frequency is given by the difference of energies for two states and some order parameter, which is equal to mz squared taken as an expectation value over the ground state. If this is satisfied, we actually formally obey Watanabe-Oshikawa theorem and still get a time crystal in continuous time. So the key ingredients, the energy difference is constant. These are not degenerate states. The oscillations must survive in the thermodynamic limit. That's a very strict condition, which again we need to satisfy. And the states that are coupled will be orthogonal. How do we construct these states? For instance, we can take an eigenbasis of the total magnetization operator, which is given by different states of spins up and down. We can pick only those states that satisfy conditions. And one way is take E naught as a superposition for some coefficients C of the computational basis states. To satisfy the condition of orthogonality of two states, we will demand that magnetization in total is 0, which means the number of spins up and down should be equal. And one possible way to satisfy this is take a GSZ state. So GSZ state will be the maximal entangled state, geometrical entangled state with all spins up plus all spins down with the normalization prefactor. And we will have the action of G plus, the action of MZ on G plus will give us G minus and return us back. So these are two coupled states through magnetization operator, and these are macroscopically entangled states. So that's why they are Schrödinger cat states. Now that I have all the ingredients, I can write the simplest toy Hamiltonian for the time crystal and say it's just equal to the projector on the one of the GSZ states. Of course, that's not a true Hamiltonian of the physical system. And we can ask, can we actually make physically, can we write the sequence of Pauli operators that corresponds to this state? So let's try to do it. Anyone that who ever written the projector on many-body state in the Pauli operators will observe that it's highly non-local operator. So when we rewrite it formally, we observe that it contains the strings of Z operators that have even lengths, and it also contains the lengths of size n for sigma x operators with pair y sigma y substitution. So this is my recipe of creating the Hamiltonian of time crystal that obeys the Watanabe-Oshikawa condition. But how exactly can be constructed? There are many possible ways. So as long as I follow the rules specified above and add these non-local strings, I will get the time crystalline behavior. And the trick is to include couplings of the following form where all spins are connected. So that's very strict condition, because if I say it's valid in the thermodynamic limit, how do we even couple infinitely many spins in the single term? But that's what formally is required for satisfying Watanabe-Oshikawa condition. And I also should mention just power law decay won't be possible because it falls in the category of no-go theorem. So if we want to really construct the Hamiltonian, it should really involve macroscopically many spins. But we also try to answer the question, what will be the most local Hamiltonians that satisfy this condition. And we can only answer it for specific problem, for instance, Hamiltonians that contain GRZ state in the ground state. And it was solved before in the paper in this PRL from 2011, where the authors answered that the shortest range of interaction to have GRZ states and to have them non-overlapping, but also non-degenerate, you need to couple at least half of spins in the system. So you will introduce the nearest neighbor interaction that makes the two states non-degenerate, but you will also couple n/2 spins in the system. And with this, you have the non-local Hamiltonian for time crystals, but which is not a toy model anymore. We summarize these results with Valery Kozin in the following PRL paper, and we also asked what will be the properties of Hamiltonians for time crystals. One property that we can look at is stability to perturbations. If we include magnetic fields or maybe two local couplings, will we change the response of the system? What happens to the correlation function? And what we observe that oscillations are stable. It's easy to understand because we demand the evolution that is based on maximal entangled states that involves all spins. So it's very difficult to break it with just single terms in the Hamiltonian evolution. Second question we try to answer is what happens at finite temperature? And if we include finite temperature, there will be a part of the correlation function from excited states. And that really starts to change our response. There will be some high frequency components, and we observe that time crystal can melt if you go to the infinite system size. So these were all finite size calculations. So it gives us a hint that if you want a genuine time crystal in closed system, you need to stay close to zero temperature. Finally, you may ask, okay, that was very idealized closed quantum system, but what about environment? Can we actually have this same physics in the presence of environment? And the answer is no, because if we actually demand that there are GRZ states that will be transformed by Hamiltonian evolution one to another, these states will decay exponentially fast in the system size. So if you want to have a thermodynamic limit and you have some small coupling to environment, even infinitely small gamma will destroy these oscillations. So in some sense, if you demand ideal quantum time crystal, you also need to say, how do I implement this ideal quantum system? And there are not many that we actually know, but one possibility is a fault-tolerant quantum computer, because if you can correct for errors, that will be the example of ideal quantum system. And if we look at the way how fault-tolerant quantum computers are realized, for instance, with the toric code, we see that they require strings of operators. So we have physical operators X and Z, and the logical operators will correspond to strings of these operators. So in some sense, the operation of fault tolerance will be very much related to what we find for idealized time crystals. And this is an interesting question for the future research. Can we relate the two? There were also the discussion of, should we even bother to write down effective Hamiltonians for time crystals, because they are unphysical, because you neglect retardation? How can you even couple all spins together? And the conclusion was that, okay, the Floquet crystal is the only genuine time crystal. My answer will be that if we want to really understand the time crystalline behavior, we need to agree on the definition. And in fact, there shouldn't be just a single definition of time crystal. So one, you can ask, what's the idealized system? And if you have a closed system like a fault-tolerant quantum computer, how do you observe time crystalline behavior there? What if you actually change the definition and make it operationally useful? Can it operate at finite noise? And what useful effects of coherence will bring to spectroscopy and measurements? So these are all the questions we can ask and study from very different perspectives. Finally, I will just mention that the example I have shown is actually related to discrete time crystals, because if I study the effective Hamiltonian for the sequence of discrete time crystals, I will recover exactly the same shape of Hamiltonian. So I will write it down as a matrix, and this matrix will couple the states, many-body states, in the form of GSZ states. So in some sense, what discrete time crystals do for spin systems, they mimic the effective Hamiltonian, which I have shown, and include the strings of different spins. And with this, I come to a conclusion. I would say that quantum time crystals are fascinating, and they can be studied from different points of view depending on the definitions. So if we go to very strict definition of ideally closed quantum system and impose Watanabe-Oshikawa conditions, we can break it if we use long-range interactions. But if we relax this condition, if we add the dissipation and drive, we can get some other phases of matter. And staying with the idealized system, we could also ask the question, can we relate time crystals to fault-tolerant quantum computation? And can we use it in some protocols? So with this, I will thank you for attention and we'll be waiting for questions.
So thank you very much for perfect timing. So please raise your hands if you want to ask a question. So maybe let me start. Let me be the first. Actually, we know that there is a no-go theorem from Watanabe and Oshikawa. And so that means that for systems with two-body interactions, spontaneous breaking of the continuous time translation symmetry is not possible in the ground state. And you have shown that with actually multi-body interactions, long-range multi-body interactions, it is possible. One of the important ingredients is that you need the gap in your system, but the presence of the gap is not sufficient. Can you give us some intuition? What is different in your system that in your case it is possible, but in the typical situation, even if you have a gapped system, it is not?
Yes. So the intuition is the gap is important because the gap gives you oscillations. If the states are degenerate, there will be no oscillations for the correlation function. But the trick of Watanabe and Oshikawa condition is we want to divide the correlation function by volume squared. So whatever oscillates must be macroscopic, must involve many spins. And if I had relaxed this condition, if I didn't divide by the volume, but renormalize it in some other way, I could live with a smaller range of interaction. So not this all-to-all interaction, but asking that correlations, so your Hamiltonian must update all spins simultaneously. That's a condition, because only then it survives if you divide it by the volume. That's the cruelty, I would say, of Watanabe and Oshikawa condition, that you want all spins to talk to each other simultaneously. And relaxing this condition, you will actually make it like you don't need to update all spins, and I would say it will be more like will have more operational meaning in this condition.
Okay, thank you. So still there is a chance for questions. We have time. So if not, I will ask second question. And because concerning the, let's say, the resistance of your system to non-zero temperature, it turns out that actually only at zero temperature you can observe time crystal behavior. And as far as I understand, in your system, what is important is that you don't have that the ground state and the first excited state are not degenerate. My question is, is it possible to, let's say, invent such a Hamiltonian, also, by changing this, let's say, properties of highly excited states, so that your system would be resistant for non-zero, for, let's say, even in non-zero temperature?
I believe yes. We tried to do it and couldn't prove that it's impossible, but also couldn't disprove it. So the problem is not even the degeneracy. You can come up with Hamiltonians where you have like spacing between levels such that there are oscillations. The problem was what happens with the order parameter. Will it decay as you grow the system larger and larger? Because if we just do the simulation, we observe that the prefactor in front of the correlation function was decreasing as you increase temperature. So you can still you still have oscillations, but the magnitude of these oscillations will decrease as the system grows. And that's again one more condition by Watanabe and Ishikawa, that everything should remain oscillating in thermodynamic limit.
Okay, thank you very much. I think we have to switch to the next talk. Thank you, Sasha.
Yes, thank you.
And now let me turn. I hope. Okay, the next speaker is Vladimir Eltsov. Vladimir, you can share your screen.
So do you
Great.
see?
Okay, so now the floor is yours. You can start.
Okay, so thank you very much for inviting me to present our work on superfluid time crystals. This is done at Aalto University in Finland, and this is experimental work. So our time crystals are actually Bose-Einstein condensates of Magnon quasiparticles, which exist within superfluid helium-3. And I will explain what are these Magnons and how we make a Bose condensate of them in a trap within a superfluid, and how we observe this condensation. Its manifestation is that spins or magnetic moment of these Magnons, their magnetic excitations, spontaneously develop coherent precession. So all combined spin or magnetic moment is precessing around external magnetic field without any external drive. And this breaks a continuous time translation symmetry, and so that makes these Magnon condensates to be time crystals. And we can actually make two of these time crystals in close proximity, and they will precess coherently at their own frequencies, which are close but slightly different. And since these Magnon condensates are actually possess spin superfluidity, then due to the interaction through this weak link here, we observe the Josephson effect or population oscillations between these time crystals, while this continuous precession remains time coherent. And we can also arrange such situation that during time evolution, the precession frequencies of these two time crystals will actually cross. And then we observe some dynamics which we interpret as a Landau-Zener equivalent of Landau-Zener transition in this time crystal system. So this experimental work was mostly done by my former graduate students and postdocs, and the time crystal aspect of it was most important in the work by Samuel Auti, who is now at the University of Lancaster. And we enjoy theoretical support from Grigory Volovik and his postdoc Jaakko Nissinen. Yes, so as we heard many times already, and we all know here that time crystals supposedly break time translation symmetry, and in original idea continuous time translation symmetry. And to limit the number of possible systems, typically only many body interacting systems are considered. And I'm coming from quantum fluids and solids community, and QFS community has immediately an answer, a superfluid. In superfluid, you can introduce this macroscopic wave function or order parameter, and the phase of this wave function will wind continuously with the frequency defined by chemical potential. But as we also know, that if you have isolated a piece of superfluid, then its phase would be not observable. And this is a kind of general, also general argumentation through this no-go theorem that if you have a ground state of a quantum system, and then you can have this perpetual observable motion in it. So there were ways to go around it found, and one of them, which is very wide, is discrete time crystals. So breaking of discrete time translation symmetry set by the drive. And we actually also have some work towards this direction, but today I'm talking about breaking of continuous time translation symmetry. So another way to go around this no-go theorem is to relax slightly this requirement for the ground state. So if we can make a superfluid from metastable particles, so that we will have Bose-Einstein condensate of some quasi-particles, for example, then ideally such system will be characterized by two very distinct time scales. One long time scale is the actually decay of the number of quasi-particles. But there will be some much shorter time scale, which corresponds to equilibration within the system of quasi-particles. And if this time scale is really much shorter than this one, then at some intermediate time scale, you can consider system with almost or constant number of these quasi-particles and look for the ground state of this subsystem at fixed number of particles. But since this will be not a ground state of the whole system, then this no-go theorem is not applicable. And our choice for this superfluid made from metastable particles are magnons within superfluid helium-3. So magnons come as quantized spin waves, and a usual transverse spin wave is the precession of spin around the equilibrium direction along the magnetic field, which propagates as a wave. So precession with certain frequency omega, which propagates as a wave with a certain wave vector k. And formally, magnons are they introduced like through Hallstein-Primakov transformation from spin to boson operators. And this way you find what's the number of magnons operator, and then the magnons have spin minus h bar, and the magnon density, which is related to the tipping angle of spin or magnetization. Of course, to have this precession to propagate as a wave, one needs to have some interaction between spins, and in different systems it comes from different reasons. And so in helium-3 it appears the following way. So helium-3 is a Fermi system, so it goes superfluid through Cooper pairing, but it's unconventional pairing. It occurs in a state with spin 1 and orbital momentum 1. And so order parameter is 3×3 complex matrix corresponding to 3 projections of spin and 3 projections of orbital momentum. And in particular B phase of superfluid helium-3, which I'm looking at here, the so-called relative spin-orbit rotational symmetry is broken. So Cooper pair, they have spin and orbital momentum. And what happens in the B phase, that the direction of orbital momentum and spin are connected by rotation through over some axis n by some angle theta, and this rotation is the same for all Cooper pairs. And the matrix of this rotation comes into the order parameter. And in the absence of spin-orbit interaction, the energy doesn't depend on n or theta, and so these are soft modes of order parameter. And actually, these Nambu-Galstone modes, they correspond to coupled motion of spin and this rotation matrix of n and theta, and these are these spin waves in helium-3b. They come as collective modes of the order parameter. And n as a unit vector has 2 degrees of freedom, and its motion corresponds to transverse spin waves, which will with this spectra, and in the absence of external magnetic field, they both will have zero energy, zero momentum. But if this symmetry is broken by external magnetic field, then one of the modes gets the Larmor gap, and it's called optical magnon, and that's what these modes which we consider in this talk. And what's important for producing Bose-Einstein condensates of these magnons? Few things. First, these quasi-particles are very light, so there is no problem of getting enough density to achieve Bose-Einstein condensation, especially that one anyway need to be at sub-millikelvin temperature for helium-3 to be superfluid. The second important thing is that these quasi-particles decay or thermalize to the ground state of the whole system through interaction with fermionic quasi-particles, with Bogoliubov quasi-particles in superfluid. And since helium-3b has gap delta, then the number of those fermionic Bogoliubov quasi-particles in bulk decreases exponentially, and so lifetime really increases exponentially with decreasing temperature, and lifetime of 15 minutes have been demonstrated. And third important ingredient, that actually in helium-3 there is spin-orbit interaction, and its strength is characterized by so-called Leggett frequency omega b, and that means that energy does depend on the direction of n vector here, and that means by manipulating the magnetic field and the direction of n vector, we can create a trap for these magnons within the superfluid bulk. And that's how our experiment looks like. So we have a glass container filled with helium-3b, and using the magnetic field profile, we create a trap in axial direction for magnons using Zeeman energy, and using boundary condition for this n vector distributions called texture, which is vertical in the axis of the sample and have some angle at the surface of the cylinder, we create a trap in the radial direction. And overall, the trap is nearly harmonic. So what we do then, we create magnons by radio frequency pulse. We tip the magnetization, and decreasing the Z component of magnetization of spin means that we create magnons. And of course, after original tipping pulse, all the magnons created are coherent, so they have the same phase. But since they exist in this non-homogeneous magnetic field, their precession starts quickly to dephase, and also this inhomogeneous texture has the same effect. And so the signal is very quickly lost. But what happens later, as magnons get collected to the ground state in this trap, this precession is magically refocuses, and we end in the state where all spins precesses with the same frequency and coherent phase over the whole volume. And this state is characterized, one can also introduce this macroscopic or condensate wave function. And it turns out that the modulus of this wave function is transverse magnetization of the condensate. the precession frequency plays role of chemical potential, and a precession phase plays role of the phase of this wave function. And so all components here are observable remarkably in experiment. And so that's how this looks from a real measurement. So here we have the pumping and dephasing. You see it's very short on this time scale. And then this condensation on the ground level of the trap happens within this equilibration time. And what we see here is this sinusoidal signal from the pickup coil, which corresponds to the coherent precession of magnetization. And by that time, of course, there is all memory of the pumping pulse is forgotten here. So we believe this state is a time crystal, so we can have a kind of time crystal checklist. So it's certainly many-body interacting system, and time crystal formation happens as a phase transition. Here, this Bose condensation, certainly externally observable. So the period is internally regulated and robust to perturbations, pump, and just in a moment on the next slide about this. And it's not a ground state of the complete system, but it's ground state of the relevant subsystem of this Magnon subsystem in a trap, and dissipation doesn't affect the periodic motion. It has no relevance to this period, as I will explain on the next slide. But eventually, of course, the number of Magnons decays. So we actually almost never look at our experimental signals in this time domain. So what we do, we have a signal in a short time window, then we make a Fourier transform, and then this coherent precession gets a very sharp peak here. And then, as you see here, that actually when it's plotted like this, the signal, then you see that actually frequency slightly changes over the time. It increases here, well, a little bit on the level of 1 megahertz of precession, but this is exactly this internal regulation of the period via spin-orbit interaction. What happens here is that this spin-orbit interaction, it acts from texture to magnons, but also acts other way around. So, and this texture, orbital texture in superfluid helium-3, it's not rigid. It can yield under the action of spin-orbit interaction. And so this precessing magnetization favors n oriented vertically here. And when we increase the number of magnons in the trap, then actually the trap gets wider, and the chemical potential lowers, and the chemical potential means the precession frequency, as I mentioned. And so that means that larger number of magnons precession frequency is lower, and then it increases, and dissipation has nothing to do with it. So this time crystal, Magnon BEC time crystals turned out to be a very useful tool to measure various things in the superfluid helium-3. So they are sensitive to fermionic quasi-particles. So one can probe, for example, this surface states in the topological superfluids. They're sensitive to the bosonic collective modes through these decay processes. And then there is one particular collective mode which is called light Higgs, so can be observed this way. They're sensitive to the quantized vortices. So we have been using them to measure quantum turbulence. So tangle of these reconnecting vortices moving to this condensate region and changing signals. And also they can actually move around the sample carrying this trap with themselves, or textural trap with themselves. And in this way, they actually simulate or implement exactly the Hamiltonian of one of so-called Q-balls models in high energy physics. So, but the thing which is I want to kind of discuss here at the rest of this talk is interaction between time crystals. So, as I mentioned, we have these two time crystals, and or we can create two traps for the magnons, and we can fill them simultaneously, and then we have these two traces from time crystals here. Sorry for different color scheme. So, for this amplitude of Fourier transform, And as I mentioned, we can extract various properties here: frequency of precession, which would be chemical potential, phase of the precession, and also the number here, or the number of particles in this condensate. That I will show on the next slide. And well, basically these two time crystals evolve, nothing special here, but you see here the sidebands. And these sidebands we interpret here, as you know, in Fourier transform. If you have modulation, amplitude of frequency modulation, then this appears as a sideband, and so we interpret those as this population oscillation between these two condensates. So in the very general weak link model, yes, between two states with wave function corresponding to bulk and surface condensates with some coupling K, it's rather easy to get that there will be this AC Josephson, DC Josephson effect when the population of there is a current from one condensate to another proportional to sine of the phase difference, but this phase difference increases with the difference of the precession frequencies, and that corresponds to periodic oscillations of population of the condensate to AC Josephson effect. And the distance between the sideband in Fourier transform corresponding to the modulation to the main carrier frequency is frequency of the modulation. And as you see, the frequency of the modulation is the difference of chemical potentials in the AC Josephson effect. And for these time crystals, for these time crystals, the difference of chemical potentials is just difference of the frequencies of precession. So we should have this frequency to be equal to this frequency. And we can check this, and that's indeed is true. So this sideband appears because the window of Fourier transform is longer than the oscillation period. We can, of course, analyze the signal on the time scale, which is smaller than the period of this AC Josephson oscillation. And then in the bulk, we have this nice population oscillation with a proper period, as you see. But for the surface condensate, we observe this very strange thing, which is actually have twice period or frequency. So here we observed some new type of Josephson effect, where one of the components oscillate actually with double frequency. It turns out that it's not, and the explanation comes from the fact that when I was saying that our signal is proportional to the amplitude of wave function, so to square root of the number of magnons, there it was oversimplification. Naturally, the spin which is closer to the pickup coil will produce a bigger signal, and so also geometry with respect to NMR coils enters into the picture. And what happens is that when this number of particles in the big bulk condensate oscillate, it also changes the trap, as I explained previously, not only for itself, but also for the surface condensate. And that changes the geometry of the condensate with respect to pickup coils and changes the signal in the pickup coils. So what we did the simulation of all these three-dimensional textures of the wave function in these traps and the signal they involve in pickup coils, and imposed this expected AC Josephson oscillations there with the same magnitude and opposite phase to the surface and bulk condensate. And then we found this doubling of the measured signal. So that's the interpretation of the signal, but the Josephson effect is just normal. So in a sense, our time crystals, they're doubly superfluid. So they exist within the superfluid, but they also demonstrate spin superfluidity by themselves. So in the previous picture, the frequencies of these two precession frequencies of these two time crystals were separate. But since the trap for the bulk condensate is more flexible, and for the surface condensate, it's more rigid due to presence of the free surface, which stabilizes this surface trap, we can arrange so that during the time evolution, the frequencies of these two time crystals, they cross. And that's how this row sliding Fourier transform look like here. So this is bulk condensate, which is here on this side and here on that side. And this is surface condensate, where frequency is almost independent on time. So what happens here? So we have here like two-level time, macroscopic two-level system made from these two time crystals. And what we can expect here, that there is an avoided crossing here, and that can be confirmed by solving appropriate equations. And now if we actually look at the populations of this lower energy state, which is first corresponds to bulk and then in the surface, and of the higher energy state, which first corresponds to the surface condensate and then in the bulk, then what will, as a function of time, then we will see that this there is this population of the lower energy state, and so that it's almost smoothly transfers from this bulk condensate to the surface condensate here. But there is a small part of population is actually going to the excited state here, and this is square root. That's why this change here is so much different. So that smells like Landau's inner transition. The only thing here is a complication that if one actually calculate this probability in this particular case, we can figure out this, one seems that one can figure out this frequency change from this plot and coupling constant, either this splitting or for the amplitude of this sideband, then we get complete mismatch in numbers. So in experiment, we get like 1% transfer to excited level, while according to this well-known formula, there should be essentially no transfer of population due to this very slow evolution of frequency or chemical potential. And to understand that, we actually did the simulations of this two-level time crystal system. And so this is a slightly different experiment where only lower energy level state is populated, and then everything you see here in the higher energy state comes due to this transition. And this is simulation, which actually reproduces very well the behavior of the experiment, with coupling being fitting parameter here. And also the so-called filling factor for NMR measurements. So how much actually this psi produce experimental signal, also fitting parameter. And looking for simulation results, we actually find what's the problem. It exactly comes to the fact that this precession frequency here and its change is internal property of the time crystal.
Vladimir, 5 minutes left.
Yes, I'm next slide is conclusion. Yes. So and then exactly what happens here is that when frequencies of these two-time crystals comes very close to the so-called Rabi regime, where this frequency difference is smaller than the coupling, then they start this very fast Rabi oscillation, and this couples through the trap creates a very fast actually change of frequency. And now, if one put this into the Landau's inner formula, then one get the expected kind of transfer to the excited state, which one see in the experiment. But if one actually look at this slow change here, that really gives a wrong result. And so I'm skipping the movie, and so I'm coming to the conclusions. So Bose-Einstein condensate of Magnon quasi-particles, which is forming on the ground level of the trap between superfluid helium-3, is manifested by this coherent precession of magnetization, which spontaneously break continuous time translation symmetry and represents a time crystal. And interacting time crystals, they demonstrate the Josephson effect conforming to the spin superfluidity. And I stress it, during all this time evolution, they do this 10 millions precession periods, keeping the coherent phase. And this two-level time crystal system show dynamics, which is kind of very often occurred in two-level time systems, such as Landau's inner tunneling. And the fact that this precession period here is internally regulated through the time crystal properties plays essential role in controlling probability of transition between levels. And given that these things are keep the coherence over a long time, that you can have Josephson effect and some features of two-level systems there. The question is, could one use them? This question has been also asked before during this day. Could one use these features to invent some quantum devices based on time crystals? And one nice feature about spin-coherent time crystals is that they probably exist even room temperatures. There are claims that there are some magnetic materials where the similar phenomena can be observed at room temperature. And then, of course, that will be very nice for quantum technology. So thank you very much for your attention.
Thank you. So please ask questions. Please raise hands if you have. I can't see any hands. Okay, maybe again, let me start asking questions. Okay, in your system, first of all, the number of magnons are not conserved because this is not the
yes, on a global scale, it's not conserved. Yes. So, but within this observation time here, it is essentially conserved. But of course, in reality, it's not conserved. And
yes, and
okay,
as far as I understand, you know, there is a strong interaction between these two time crystals. That corresponds to the nearly the same frequency of the precession of both of the condensates.
Yes.
And this is my question is because one can also consider other system, other coupling of different time crystals, for example, even discrete time crystals. In this morning, actually in Angelo talks, we saw that it is possible to couple discrete time crystals by, let's say, by some, let's say they could interact. Do you expect that the effect of the interaction will be also the strongest, the closer frequency of the driving these two separate time crystals is, or this is?
Of course, it's difficult to make this general prediction. I can only say that maybe I should clarify that this coupling actually between these two time crystals, it's changing during evolution when frequencies change, but its magnitude is not the strongest at this when frequencies are the closest. It's just that the interaction, which may be the same whether frequencies are far or nearby, have the strongest observable effect when the frequencies are close by, in our case. So maybe that what I can, maybe that can be projected to other systems. So yes, if you have interacting time crystals, then it's kind of maybe expected that when the frequencies are close by, then the effect of this interaction would be the most profound.
Okay, thank you. We have a question. Okay, Vincent Liu, please unmute and ask a question.
Great, very exciting talk. So I just want to have a question, something you might have talked about, but I catch that. So what sets the time scale of the emergent period of the Magnon time crystal? You said it's internally, right?
Yes, so it's a competition. Let's see. So basically, it's a ground level on this trap, yes, and so the kind of the main the trap is of course prepared by experimentalists, but then the time crystal itself can make a small adjustment to this trap by modifying the texture. So this 800 kilohertz precession frequency is set by us, by experimentalists, but then the time crystal is adjusting its frequency depending on the number of magnons you put into condensate.
Is that a way to let me backtrack a little bit. So it's very nice to see the measurement to test the superfluid, which is essentially with the U1 symmetry broken, which is associated with the approximate conservation of particle number, right?
Yes.
So is that a way to test this time crystalline symmetry breaking, some effects due to that? Have you thought about it? Yeah.
Absolutely. So thanks for this question. So because I have a slide after this conclusion.
Okay.
Yes. So that let's see. It's yes. So there is this symmetry breaking. So we can expect this Nambu-Galstone mode. Yes, which would be we can call a phonon in a time crystal. Yes, and yes, this mode exists. So it corresponds to oscillation of the soft variable of this phase of precession, and it can be observed on the experiment. This is like with double excitation or demodulation techniques. You can observe the standing wave of this mode in the sample and then the next excited state. So yes, it certainly can be observed.
Thank you.
Okay, thank you. I think we have to stop at this moment. Now we have a break, nearly half an hour, and at 5 p.m. we will meet again during the poster session. There will be breakout rooms associated with each poster, so we can travel between different posters. And okay, we have a break. Thank you.